You are living through the single best moment the universe will ever have. Not the best moment for you. The best moment, period. And it is already ending. Here is the part nobody tells you. The night sky you looked at last week, every star in it, is not a permanent fixture of reality. It is a flash. A spark that lasted a heartbeat on a clock so vast that comparing it to a human life is like comparing a human life to the time it takes an electron to spin once. And that spark is going out. Not might go out. Not could go out under the wrong conditions. Will go out. It is written into the deepest law we know. That law has a name, the Second Law of Thermodynamics. It says, in plain terms, that disorder always increases. Energy always spreads out. Hot things cool down, ordered things fall apart, and nothing runs backward on its own. Drop an ice cube in warm water and it melts. You have never once seen the reverse happen, water spontaneously freezing itself into a cube while the surrounding liquid heats up. That small kitchen table observation is a crack in the wall of a much bigger structure. Scale it up. Scale it up past galaxies, past superclusters, past every star that has ever existed or ever will. The same rule applies to the entire universe, because the universe is not a stage that exists outside of physics. It is bound by it. Think of the universe as a wound-up machine. At the beginning, it was wound as tight as it will ever be, hot, dense, bursting with usable energy. Every star that lights up the sky right now is running on that original wind-up, like a clock spending down the tension in its spring. And a clock spring does not rewind itself. Once the energy spreads out into a smooth, useless, low-grade hum, there is no getting it back. Physicists call the final state heat death, and it is not a metaphor. It is a prediction, made of the same mathematics that gets your GPS satellite to the right coordinates and your microwave to heat your dinner. This isn't science fiction. This is the most well-tested branch of physics we have, extrapolated honestly to its logical end. So here is the deal we are about to make with you. We are going to walk through the death of everything, literally everything, down to the last stray particle, in the correct order, at the correct scale, using real numbers. It will get colder, darker, and stranger than almost anything the human mind is built to hold. Stay with it, though, because the ending is not what you think. The point of walking through the funeral of the universe is not despair. It's the opposite. But you have to earn that ending. Let's start the clock. One more thing before we do. Every number you're about to hear is going to sound made up. It isn't. These aren't guesses pulled from a science fiction script. They come from the same equations that predict the orbit of every planet, the decay rate of every radioactive isotope, the behavior of every particle inside a functioning nuclear reactor. When physicists say a black hole will take 10 to the 100th years to evaporate, that number falls directly out of calculations about quantum effects near an event horizon, physics that, in a much gentler form, already underlies working technology on Earth today. The scale is different. The physics is not new physics invented for this video. It's the physics we already trust, just run forward for an obscene amount of time. Right now we are in what's called the stelliferous era, the age of stars. It has lasted about 13.8 billion years so far. That number feels enormous. It is not. Compared to what's coming, it is the first 3 seconds of a movie that runs for longer than you can write out in a normal-sized font. Stars are factories. They take raw hydrogen, fuse it under crushing gravity, and manufacture light, heat, and eventually every heavier element in your body, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now. You are, quite literally, stitched together from the ash of stars that exploded before the sun existed. That is not a poetic flourish. It is a settled fact of nuclear astrophysics. But factories run on fuel, and the universe's fuel tank, those stars burn recklessly. A blue supergiant can exhaust its hydrogen in a few million years, a blink, cosmically speaking, and end in a supernova that briefly outshines its entire home galaxy. Those are the fireworks. But the real story of the far future belongs to the misers, red dwarfs. Red dwarfs are small, dim, and thermodynamically stingy. They fuse hydrogen so slowly and so efficiently that the coolest, smallest ones will keep glowing for somewhere in the neighborhood of 10 trillion years. 10 trillion. Write out 13 zeros and you're close. That is roughly 700 times the current age of the universe, and it is only the beginning of a single star's life, not the end. Now project forward past that number, past the point where every red dwarf, one by one, sputters through its final reserves of hydrogen, past the point where new stars stop forming at all, because star formation requires cold, dense clouds of hydrogen gas, and those clouds are a finite resource too, used up, locked into dead stellar remnants, and never replenished at the rate they once were. Somewhere out past 10 to the 14th years, a 1 followed by 14 zeros, the last true star in the history of the cosmos will fuse its last atom of hydrogen, flicker, and go dark. Sit with that for a second. Not the last star in our galaxy. The last star that will ever exist, anywhere, in the entire observable universe. After that moment, there is no more starlight. Not dimmer starlight. None. The stelliferous era, the only era in the entire lifespan of the cosmos that will ever contain a visible night sky, closes its doors permanently. Every future observer, if there ever is one, will look up into a sky with nothing in it at all. We are living inside the credit sequence of the only chapter in the universe's story that comes with a soundtrack of light. Think about what that actually removes from existence. No sunrise, because there is no sun and never will be another. No warmth radiating across a planet's surface, because there is no star close enough to provide it. No photosynthesis, no green in anything, no cycle of seasons, because none of that machinery works without a nearby furnace of fusion pouring energy into a nearby world. Any planet still drifting through space at that point, assuming it hasn't already been flung out of orbit by the slow gravitational chaos of dying star systems, becomes a frozen rock in permanent night, lit by nothing but the faint, indirect glow of a few remaining embers scattered unthinkably far apart. And that's still the more forgiving stretch of what's coming. And this is where most people assume the story of cosmic death ends. Everything just goes dark, roll credits. It doesn't. Darkness isn't an ending. It's a transition into something far stranger, because matter itself does not simply vanish when the lights go out. It lingers. It decays. And what's left behind is one of the eeriest landscapes physics has ever described. Welcome to the degenerate era, the long, cold afterlife of matter. This stretch of time doesn't just outlast the stelliferous era, it dwarfs it so completely that comparing the two is almost an insult to the word comparison. This era runs from roughly 10 to the 14th years out to somewhere around 10 to the 40th years. If the age of stars was a single grain of sand, the degenerate era is a beach that stretches past the horizon of your imagination. What fills this beach? Corpses. Cosmic corpses, to be precise, and there are 3 kinds. The first are white dwarfs, the leftover cores of stars like our own sun, once they've shed their outer layers and stopped fusing anything at all. A white dwarf doesn't explode or collapse. It just sits there, radiating away its leftover heat like a dying ember, for an unimaginably long time. Eventually, every white dwarf in the universe will cool all the way down to the temperature of its surroundings, becoming what's called a black dwarf, a dead, dark, Earth-sized ball of degenerate matter, radiating essentially nothing, doing essentially nothing, forever. Here's the unsettling part. No black dwarf has ever actually formed yet. Not one. The universe, at 13.8 billion years old, is still far too young. The very first black dwarf won't exist until roughly 10 to the 15th years from now. We are so early in cosmic history that the first dead star hasn't even finished dying. The second type of corpse is the neutron star, the collapsed remains of a star that went out in a supernova, so dense that a teaspoon of its material would weigh about as much as a mountain on Earth. And the third is the black hole, gravity's final, most complete victory over matter, a region where the rules of ordinary physics simply unimaginably vast, unimaginably empty, populated only by these cold, dark, silent remnants, drifting further and further apart as space itself keeps stretching. Every few trillion years, by sheer cosmic coincidence, 2 of these dead stars might drift close enough to collide, producing one last, brief, violent flash of light in a universe that otherwise sees none. Imagine floating in that dark for longer than the entire history of stars up to now, waiting, and being rewarded with a single flicker before the silence swallows it again. That is what passes for an event in this era. There's something almost mournful about picturing it directly. A neutron star that once powered a supernova bright enough to be seen across an entire galaxy now sits in absolute blackness, absolute cold, absolute silence, doing nothing but existing, for a length of time that makes the entire age of the dinosaurs look like a single tick of a stopwatch. Occasionally, extraordinarily rarely, gravity pulls 2 of these corpses together in a final collision, briefly lighting up a patch of otherwise permanent dark before it fades again into the same silence that has already lasted longer than anything you could reasonably picture. The universe, by this point, has become less a place where things happen and more a place where things wait. But even these dead husks are not truly permanent, And here is where the story turns genuinely strange, because we start dismantling the very idea of solid matter. Many models in particle physics, grand unified theories that try to explain how the fundamental forces connect, predict that the proton itself, the very particle sitting at the core of every atom, of every rock, every planet, every body that will ever exist, is not perfectly stable. It may decay. This hasn't been observed yet. Experiments have only set a lower limit on how long it must take, somewhere north of 10 to the 34th years. But if protons do decay, then given enough time, and in this story, we have nothing but time, every single atom, every stray fragment of a dead star, every last brick of ordinary matter left in the universe will quietly dissolve. Not explode. Not burn. Just fall apart, one particle at a time, until literally nothing solid remains anywhere. By around 10 to the 40th years, the era of matter, the era where stuff in any conventional sense exists at all, comes to a close. What's left is a universe with no atoms, no rocks, no stellar remnants. Just a diffuse fog of subatomic debris and radiation, drifting through a space so vast it makes the earlier emptiness look crowded by comparison. You'd think that after obliterating light, then obliterating matter itself, there would be nothing left to kill. You'd be wrong. There is still one more titan standing in this universe, and it is the most powerful, most feared object physics has ever discovered. Even black holes are not forever. For a staggering stretch of cosmic time, black holes are the last real structures left in existence. They're the final holdouts of gravity's total dominance, having consumed nearly everything else: stars, gas, dust, even other black holes, merging together into monstrous supermassive giants at the centers of what used to be galaxies. If you had to bet on one thing outlasting the rest of the universe, betting on a black hole seems like the safest wager in cosmic history. You would still lose that bet. In the 1970s, physicist Stephen Hawking worked out something that seemed almost like a contradiction, a place where quantum mechanics and gravity collide, and quantum mechanics wins. Right at the edge of a black hole, the event horizon, pairs of virtual particles are constantly popping in and out of existence, as they do everywhere in empty space, for tiny fractions of a second. But at the horizon, something strange can happen. One particle of the pair falls in, and the other escapes. From the outside, it looks exactly as if the black hole itself is emitting particles, glowing, faintly, into space. This is Hawking radiation, and the consequence is almost poetic in its cruelty. Every time a black hole glows like this, it loses a tiny sliver of mass. Slowly, imperceptibly, it is evaporating. Here's the truly counterintuitive part. Big black holes evaporate slower than small ones. A black hole with the mass of our Sun would take about 10 to the 6 to 7th years to fully evaporate, a number so large it's almost meaningless to say out loud. But the real monsters, the supermassive black holes sitting at galactic centers with masses billions of times that of the Sun, will take on the order of 10 to the 100th years, a number known, informally, as a googol. One followed by 100 to actually picture that number. You cannot. Nobody can. It isn't a very large number in the way a trillion or even a googol's baby cousin might feel large. It's a number so far removed from anything in ordinary experience. The number of atoms in the observable universe is only around 10 to the 80th, that a googol years isn't just longer than the age of the universe so far. It's longer than the age of the universe so far multiplied by itself, roughly, and then some. And that's just for the black holes to finish evaporating. Before that final moment, as a black hole shrinks, it heats up. Counterintuitively, the smaller it gets, the hotter and faster it radiates, until, in its last fraction of a second, it detonates in a final flash of high-energy radiation. A death, at least, that is quick, even if the wait for it is longer than anything the human mind evolved to comprehend. Try one more way of grasping it. If you tried to write out a googol using 1 digit per grain of sand, you would need more sand than exists on every beach and desert on Earth combined, many times over. If you tried to count to a googol at a rate of 1 number per second, the process would take vastly longer than the universe has existed so far, repeated over and over, before you ever finished. That is the number of years standing between us and the last black hole's final flash. And that's the timeline for the biggest black holes. Every smaller black hole in the universe finishes the job earlier. But earlier here is still a number too large to hold in your head. When the very last black hole in the universe pops out of existence in that final flash, somewhere out past 10 to the 100th years, gravity's long reign is finally, completely over. There is nothing left with enough mass to bend space in any meaningful way. No stars. No atoms. No black holes. Just what comes next, which is, in a way, the strangest and quietest chapter of all. We've killed the light. We've killed the matter. We've killed gravity's last champions. What's actually left when you subtract everything? This final stretch is called the Dark Era, and it is less an event and more the mathematical destination the entire universe has been sliding toward since the beginning. Picture space stretched out to an almost incomprehensible size by the relentless expansion of the universe, a stretching that, according to our best current models, is not slowing down but accelerating. Scattered through that vast empty volume is an extraordinarily thin, extraordinarily cold soup. Stray photons, the ghostly, nearly massless particles called neutrinos, and the faint decay products of everything that came before. That's it. That is the entire contents of the universe. Temperature, at this point, isn't really a meaningful concept anymore in the way you experience it. It approaches absolute zero, not zero exactly, since true absolute zero is itself unreachable, but close enough that the difference stops mattering. And here's the part that's genuinely difficult to wrap your head around. Temperature differences are what allow anything to happen. Heat flows from hot to cold, and that flow is what powers engines, chemical reactions, weather systems, and, yes, life itself. When everything in the universe reaches the same temperature, when there is no more hot and no more cold, just one uniform, frigid average, nothing can flow anywhere anymore. No energy can be extracted to do any kind of work. This state has an almost bureaucratic-sounding name for something so final: maximum entropy. Total, complete equilibrium. And here's the piece that tends to unsettle people the most: more than the cold, more than the dark, more than the unimaginable stretches of time. In a state of perfect, unchanging equilibrium, does time even mean anything anymore? Time, as we experience it, is stitched together out of change, one moment being different from the moment before it. A clock only works because its gears move. A mind only works because chemical signals are flowing from one state to another. If nothing anywhere is changing, if every point in space is functionally identical to every other point and stays that way forever, there is no longer any meaningful before and after. The universe doesn't so much end in this scenario as it does simply stop mattering whether it continues. It becomes a single, frozen, eternal instant, no different one moment to the next, because there are no more moments to be different. This is the true heat death of the universe. Not a bang, not a fire, not a war between light and dark, just an infinite, silent, perfectly still nothing, stretching on without any observer left to notice this ending is from the ones fiction usually sells. There is no final battle. There is no last civilization making a heroic stand against the dark. There isn't even a dramatic instant you could point to and call the end, the way you might point to the last frame of a film. Heat death doesn't arrive like a wall you slam into. It arrives like a tide going out so slowly that by the time the water is gone, there was never a single moment when you could say, there, that's when it happened. The universe doesn't die with a scream. It simply, gradually, runs out of differences to have, and difference, it turns out, was the one ingredient every interesting thing in the cosmos, including you, was built out of. So let's come back. All the way back, past the Google years, past the evaporating black holes, past the trillion-year twilight of the last red dwarfs, back to right now. To this sentence, on this device, on a small rocky planet orbiting a perfectly ordinary yellow star that is roughly 4.6 billion years into a 10 billion year lifespan. Here is the twist we promised you. Everything you just sat through, the darkness, the decay, the cold, wasn't meant to make you feel small or hopeless. It was meant to do the opposite. Do the math with us, one more time. The stelliferous era, the only period in the entire history of the cosmos when stars exist, when light exists, when planets and chemistry and atoms arranged in complex, thinking patterns are even possible. That era spans from roughly the first 100 million years after the Big Bang to about 10 to the 14th years from now. Compared to the full span of cosmic time, stretching out past a Google years and beyond, the age of stars isn't just short. It is a rounding error. It is, proportionally, closer to a single second in the entire history of the universe than most people would ever guess, and even that comparison undersells how narrow the window really is. And within that already narrow window, we happen to exist right now, at a moment when stars are burning, when heavy elements have had time to form, when planets have had time to cool and stabilize, when liquid water and organic chemistry have had time to arrange themselves into something capable of asking questions about its own existence. That is not a guaranteed feature of the universe. For the overwhelming majority of the timeline that reality will ever occupy, the stretch of black dwarfs and dark eras and silent, frozen equilibrium, None of this is possible. No light.
No worms.
No chemistry complex enough for a single thought to occur, anywhere. We are not living in an average moment of the universe's history. We are living in the anomaly, the exception, the brief, bright spring before an eternal winter that outlasts every number we have a name for, every sunrise you've ever seen, every meal you've ever eaten, every conversation, every mistake, every quiet ordinary Tuesday. All of it happened during a sliver of time so improbably rare that privilege barely covers it. You exist in the one thin flash of cosmic history when existing is even an option. Everything after this, the trillions upon trillions of years of darkness, decay, and stillness, will never again offer that chance to anyone or anything. So the next time you step outside and look up at a sky full of stars, you're not looking at something permanent. You're looking at a fire that is, on the scale of the universe, just being lit. And you happen to be standing close enough to feel the warmth of it, at the one moment in all of eternity when there was any warmth to feel at all. That isn't a small thing. That might be the single largest piece of luck that anything, anywhere, will ever have. Consider, too, what that luck actually contains. Not just the existence of a planet, or a sun, or the right chemistry for carbon-based life, but this exact moment. The fact that a species evolved on that planet with a mind complex enough to wonder about its own future, to do the math on black hole evaporation, to feel a small chill imagining a googol years of darkness, and then to feel something like gratitude on the way back out of that thought. Nothing in the dark era will ever have a mind. Nothing in the degenerate era will ever ask a question. The capacity to be curious, to be afraid, to be moved by an idea, all of it is packed into this one impossibly thin sliver of cosmic time, and you are spending part of that sliver right here, right now, thinking about through all that darkness first. You cannot appreciate how strange and temporary this moment is without seeing what it's surrounded by. 13.8 billion years behind us. Something on the order of a googol years of cold and silence ahead. And in between, an impossibly narrow window, the only window there will ever be, where light exists, where warmth exists, where mind can form and use that light to see something as unlikely as itself. You're inside that window right now. So is everyone you've ever loved. So is every sunset, every song, every quiet, unremarkable afternoon you almost forgot to notice. None of it was guaranteed. Almost none of eternity looks anything like this. And yet, here you are, right in the middle of the one part of it that does.